So, dear colleagues, today is our first meeting of our seminar after New Year vacation. And we have a very famous professor from France, Professor Thomas Ebbesen. He is a Franco-Norwegian physical chemist. He was educated in the United States and France, receiving his bachelor degree from Oberlin College in USA and his PhD from the Curie University in Paris. He then did research in both the United States and Japan, most notably at the NEC Fundamental Research Laboratories, before returning to France in 1999 to help build a new institute at the University of Strasbourg. He's currently the director of the Strasbourg Institute for Advanced Studies and the Jean-Marie Le Foundation, which provided, by the way, financial support for our institution to recover it after Russian bombing. He holds the chair of the physical chemistry of light matter interactions. The author of many papers and patents, Ebbesen has received numerous awards for his pioneering research, including the 2014 Kavli Prize in Nanoscience for his transformative contributions to nano-optics, and the gold medal, the highest French distinction given normally only to one person a year, for the development of the field of polyretonic chemistry. He is a member of the Norwegian Academy of Science and Letters and former member of the French Academy of Science. And his today lecture is devoted to the new field of chemistry, now called just polyretonic chemistry, that Professor Ebbesen initiated 15 years ago. And dear Professor, you can start your lecture and presentation.
Well, thank you very much. First of all, I'd like to say that my heart is entirely with the brave people of Ukraine, and I think of your country nearly every day. And I hope that the peace will return to the region soon, as soon as possible. So it's a pleasure to give this lecture on the title of my talk is Alchemy of Vacuum. Why? Because I'm going to talk about chemistry in conditions that most people are not familiar with, especially in chemistry. And this title, a lot of people have a hard time accepting this what I'm going to show you. And so I think the title is appropriate for that purpose. So to introduce the subject, I'm going to start with something very simple. Oops, I can't control the. I'm going to start with showing you just a droplet sitting on the surface. And when you are in chemistry, you generally don't learn that there are light matter interactions in such a droplet, even in the dark. And this is kind of surprising because there is. And to understand that, you have to know more about what is actually vacuum. And we think of vacuum as something empty, no space-time, but it's actually more complicated than that. So if you look back in history, people discussed what the nature of vacuum, of empty space, already 2,000 years ago, at least in Europe. And Aristotle thought there was no such thing as vacuum, while Democritus and Lucretius thought, of course, there had to be vacuum, there had to be empty space between matter. Democritus gave us notion of atoms, and so between atoms, for things to mix, there had to be some space. And it was Aristotle's view that apparently survived through the Middle Ages. And in the 17th century, people started doing vacuum experiments. This is the beginning of modern science. And people like Torricelli in Italy, von Guericke in Germany, and Blaise Pascal would have hand pumps, of course, and try to make a material vacuum in glassware. And when they did that, they were very surprised to see that light still could propagate through the glassware. And because they thought that light needed to propagate in something. And so the notion of ether came back, and which of course was a magical substance that remained after you removed all matter. Of course, these voids that you saw in glassware weren't completely empty. They were, of course, still, there was, of course, molecules and gas inside, but still, that they didn't know at the time. And so this was a surprise to them. In the 20th century, so we go to the 20th century, Einstein, of course, changed our whole view of physics and of our world around us. And with the development of general relativity and special relativity, we all learned that the speed of light is constant, that it follows the curvature of space-time. And in that view, space was just empty space. And this changed dramatically within 20 years or 10 to 20 years, when Dirac started to try to understand how things interacted at a distance. How does a positive charge recognize a negative charge? How does it? I mean, most chemists don't learn this. How does it distinguish at a distance between a positive and negative charge, for example? And in the process of trying to understand these interactions, the fields of interaction between matter, he developed what is now known as quantum electrodynamics. This is nearly 100 years ago. In quantum electrodynamics, notions like antimatter appeared, the notion that there were antimatter, and this was, of course, seen, and this made this theory very famous. So in the quantum electrodynamics view, vacuum is no longer empty. It's full of activity at all times, right here in your room, in your head, anywhere. Any space-time is full of fluctuations. And this is known in modern jargon as quantum vacuum. And this activity of space, these fluctuations, quantum fluctuations, I'll come back to that in a second, have a huge impact on the properties of matter that we take for granted, and including chemical interactions and material properties. So if you have doubts whether there's matter in empty space, you just have to look at Maxwell's definition of the speed of light in empty space. It's inversely proportional to the permittivity and permeability. The permittivity essentially is just a dielectric constant of empty space. So if empty space has a dielectric constant, it cannot be empty. And the difference between empty space and glass is only a 2/3. The speed of light is only a 2/3 difference, which means that actually empty space resembles a dielectric medium. And this, of course, is kind of surprising. So what's in there? What's happening? And to understand that, I will just now concentrate on one type of field, the electromagnetic field. And because for every force, there's a field, like nuclear forces and so forth, there's a field. And for electric and magnetic forces, it's the vacuum electromagnetic field that is determining. So when light comes out of your screen, for example, or comes out of a lamp, it doesn't just fly out as we have imagined it in a straight line, as we learn in classical physics, and go to the eye. It actually goes into a state of space, which accommodates the photons. And there are infinite number of states for photons in empty space. And all these vacuum states, as they're known, they are quantum states, and because of that, they fluctuate. They have uncertainty, because of uncertainty principle, they have zero-point energy. And so there's a bubbling of activity of all these states everywhere around us. And they determine many other properties, for example, emission. So light cannot be emitted into space unless there is a state to receive the photon. So the screen that you're looking at, the light can only come out of it because there are states in space to accept the light. You can do a very simple experiment. You can put atoms, for example, inside a confined space, a Faraday cage, a very small Faraday cage, and you can limit the emission or enhance it by changing the number of available states in this confined Faraday cage. And so the properties of an emitter is not just that of the emitter, which is what we learn in chemistry, and I'll come back to that later on. Furthermore, the emission of light is only possible because of these electromagnetic fluctuations of empty space. Without them, there will be no light emitted anywhere. So here this image on top here, a little video I'm showing you here is from a theoretician these are gluon fluctuations, but the principle is the same. This is calculated by this Australian physicist. And here you see these fluctuations that are going on right now. These are simulations, of course, but they are going on right now in your eyes, in your head, everywhere in your space around you. And these have impacts a lot of properties. Now, some people don't think that these things exist, so I just want to reassure you that such vacuum fluctuations, electromagnetic ones, have been detected directly with very fast time-resolved equipment by groups in both constant and at ETH. So coming back to the droplet I showed in the very beginning, the droplet here is held together by, if it's a hydrocarbon, for example, by van der Waals forces. And if it's a hydrocarbon, it's only dispersion forces that are holding together. And I remind you that we learn in physical chemistry, when I was a student, I learned the London dispersion forces was due to fluctuating dipoles. Actually, what generates the fluctuating dipole is these vacuum fluctuations. So one expects that London dispersion forces are very sensitive in matter, very sensitive to the interaction with these vacuum fluctuations. As I will show you in experiments that follows, that we can actually modify this interaction and modify London dispersion forces. So, sort of, if you look more generally about molecules and zero-point energy, vacuum zero-point energy, these electromagnetic fluctuations, they're involved in van der Waals forces, as I just showed you. They're also involved in Lamb shift in hydrogen atom, the famous Willis-Lamb shift, and he measured the very precise transition of the hydrogen atom, and he realized that this transition, energy of transition, could not be correctly evaluated without taking into account the presence of the vacuum field. And this he got a Nobel Prize for because it was very important at the time. Now, if you look at the famous Einstein coefficients for spontaneous emission, stimulated emission, and absorption, you will notice that absorption requires a photon, stimulated emission requires a photon, and spontaneous emission never shows anything that triggers it. But actually, since from quantum electrodynamics, it became clear that what generates the so-called spontaneous emission is the vacuum fluctuations, this perturbation of space. And this is critical. So when you think about it, if you try to do a stimulated emission experiment with molecules, for example, you know that you have to compete with spontaneous emission that is triggered by vacuum fluctuations. And you know how powerful of a laser you need to see stimulated emission, so you can imagine the importance and the prevalence of the vacuum fluctuations that trigger so-called spontaneous emission. Essentially, there's no such thing as spontaneous emission. It's a triggered phenomena that we have sort of ignored because we live in this bath of vacuum fluctuations. So all electric, and this is for chemists who might not have learned this, all electric and magnetic interactions are mediated by virtual photons. So virtual photons are generated in this process, in these fluctuations. They are transient. My understanding of it is that they are transient photons, ephemeral photons that are generated by these fluctuations. And they also are exchanged between, for example, between a magnet and a fridge door. The magnet is exchanging photons with the fridge door. It's also determining whether electric charge sees the charge of the same nature or the opposite charge at a distance. This exchange of photons allows it to generate a force. This is that's the origin of a force between negative and a positive charge attracting each other or repulsing each other without the same charge. So this vacuum field is therefore very important. And if you modify this interaction with the vacuum field, you're going to modify chemistry and material science, as I'll show you. So in the quantum electrodynamic picture of things, light-matter interactions fall into two regimes, weak and strong coupling. In the weak coupling regime, you modify the radiative properties, so how the probability of emission. And the very first experiment actually on this was done, apparently, according to physicists, by a physical chemist called Karl Drexager in Germany, in Göttingen. And in the 60s, 1960s, he placed molecules in front of a mirror, metal mirror, as a functional distance using Langmuir-Blodgett technique. And all chemists know that. Sometimes I have to explain this to people who are not from chemistry, but I assume that you know what this is. So you deposit layer after layer. And this you could do in the 60s with 9-nanometer precision. And then he looked at the fluorescence, and in the last layer, he put his fluorescent europium complex. And very close to the mirror, there was quenching because energy transfer went from the molecule to the metal. This is well known. And as he moved away from the mirror, suddenly the lifetime went down and the quantum of emission went up. And at around 100 nanometers. And then he went further away and then it dropped again and the lifetime became longer and the emission quantum went down and so forth until the molecule was far enough from the mirror that you essentially recovered the free space properties. So what does this tell you? Well, the mirror is perturbing the vacuum states around the molecule. It's sitting there's a huge mirror and it's molecule sitting very close to the surface and its environment is perturbed. And it's acting like a half a cavity, optical cavity. And so about 100 nanometers from the mirror, when the emission quantum is very high, there are lots of optical states. As the physicists say, there's a large density of optical states. And so the molecule emits much more easily. And then a little bit further away, it's reversed. There are very few states, and it doesn't emit at all, or very little. And then it oscillates like this as you move away from the mirror, eventually reaching the free space behavior. And what does this tell you? It tells you that the emission properties of a molecule or any emitter is not just that intrinsic property of the molecule or the emitter. It's a property of the molecule and in its environment of vacuum states. And this, of course, can be engineered. You can enhance the emission and change the lifetime just by playing with this notion. Now, what I'm going to talk to you now is the other regimes called strong coupling regime, where you make matter or molecules interact with the vacuum field so strongly that you generate hybrid light matter states. And so you might ask yourself, what on earth are hybrid light matter states? Before I get started explaining this, I have to show you something about coupled oscillators. Okay, coupled oscillators were also discovered in the 17th century, like many of these vacuum experiments, the first vacuum experiments. This one was by Huygens, who gave us the pendular clock. And in the pendular clock, he noticed when he made these pendulas that they would couple, they would interact and start oscillating at the same in phase. And he solved the coupled oscillator problem of the pendula. This is not very different from H plus H gives H2 with bonding and anti-bonding orbitals, the same general principle. And here's a modern version of it with sound. Comes from, sorry, it's not moving, so I don't know why it's not moving. Sorry, I'm going to move back. Try again. And you have 5 metronomes. I hope you can hear this. And they're out of phase. As you can see, they're all moving in phase after a while because they're exchanging energy through the base. And I don't know why it's not moving again, but they're moving in phase. You can hear it. They're all moving like this in phase because they are coupled. And you can also hear it, even if the movement wasn't following. And And this, some people think this looks like magic. It's not. It's just the exchanging energy faster than dissipation. That's the critical issue. And you see all these metronome moving in phase, and we're going to do something very similar with the optical field. I'm going to make electronic density of molecules oscillate in phase, and this is going to change the properties of matter. And the critical condition is that you exchange this energy faster than dissipation. And so there's a very similar phenomena ongoing between in something called J and H aggregates. A lot of chemists work with those. In H aggregates, you have molecules that are packed in the crystal in such a way that the transition dipole moments are coupled, aligned here. These two monomers here, and because they're aligned and they start and they fluctuate, because again the transitions fluctuate even in the dark. This is without any light. They exchange virtual photons, these temporary photons that exist in space, and they couple. And under the right conditions, they generate then new aggregate states, which have been used for even in old-fashioned photographic film, and have different, of course, the aggregate states have very different properties than from the monomers. This is obvious to chemists. And then now, if I replace one side with an optical resonator, I can do exactly the same thing as between two molecules, except now I'm interacting the matter resonance with an optical resonance. And in the QE quantum electrodynamic picture, these things are similar. They're treated in the same way. The optical resonance also fluctuates. And they start exchanging virtual photons. And now you get hybrid states, coupled oscillator states that are hybrid light matter states. And this, of course, is very surprising to a lot of people. When you come from chemistry, what's a hybrid light matter state? Indeed, what is it? I'll try to explain a little bit what that is, but it's an unusual notion for chemists and material scientists. And of course, but what was obvious to me was that when I first learned about this from physicists who have studied this for a long time, the only thing that came to my mind is that, well, this has to change the properties of matter and molecules. And that's how I came into this topic, and which is why I got involved trying to demonstrate this, starting 20 years ago. In the last 15 years, we've been able to demonstrate systematically that properties are changed. And now, of course, a lot of other people around the world. So I still have to, since this is an educational process, so I still have to remind you that there are these states, these hybrid light matter states are called polaritonic states. Sometimes physicists call them polaritons, but I find that confusing because that's a particle. Anyway, the polaritonic states, plus and minus, the lower state and upper state. The wave functions contain both photons and electrons, in this case, this particular example, which is an unusual concept for chemists, needless to say. The separation between the two states, P plus and P minus, is known as the Rabi splitting, and that depends on number of terms. And I'm just going to take the simplest case. You ignore dissipation for a moment, and then you see that this separation here depends on the transition dipole moments, which in molecules typically is very high, so it's very favorable, inversely proportional to the mode volume. And the mode volume is the extent of the resonance, the optical resonance. If the more it's squeezed, the smaller the mode volume is here, this V here on the bottom, and therefore the larger this term becomes. And then, so that's favorable in modern tiny structures. And then it depends on the number of photons plus 1. So when number of photons goes to 0, there still is a Rabi splitting in the dark. And this is due to the interaction with the vacuum electromagnetic field. And the virtual photons here play a role. This comes out to for specialists, this comes out to the non-commutability of the creation and annihilation operators that appear in quantum electrodynamics. Now that's for one molecule, one photon type of a situation, or one atom, one photon situation. In a normal optical resonator, we are coupling, we have resonances in hundreds of nanometers or microns. And so inside an optical resonator, we're going to place the molecules. I can put very many molecules to interact with one mode. And quantum mechanics teach us that then we have to sum over all the possibilities. The optical mode can interact with all the molecules in the cavity equally. So you have to sum over all the possibilities, and you end up with some collective coupling. You normalize, and you end up with a collective coupling with a Rabi splitting, a collective coupling. So the square root of n, the number of molecules interacting with the mode, times the elementary Rabi splitting at the molecular level. And then you also got a linear combination of dark states, what they call dark states, but they still are collective states again, these dark states. But because there's an excitation involved in here, but they are dark, and so there's no mixing with the ground state. And so these dark states also can play potentially a role in what we observe. Now, what does this mean? This means that you have collective states, that you generate tremendously large collective states inside cavities when you do this strong coupling. And what's surprising is that if you do couple electronic transitions, you see that as you increase square root of n, this separation here between the two states gets bigger and bigger. And then as you increase the concentration of coupled molecules, you can add molecules to the system, for example, and you see the splitting goes up and up, and then the emission, for example, from P minus, the fluorescence shift to lower and lower wavelength, because the splitting gets larger and larger. And so this is the presence of some molecules affect the properties of all the molecules. So if you add more molecules, you change the properties of all the molecules in the system. This is kind of surprising and unintuitive. The second thing is that these collective states run through all the molecules and therefore boost transport properties, which are very large. The change in transport properties are huge in polymers, in 2D materials, in water, ionic conductivity. We'll see that later on. So how do we do the experiment? You have a silver, you take a slide, you coat it with a little bit of silver, 10 nanometer silver. You spin coat some molecules to the silver substrate. You come with a second silver mirror, sorry, and you make sure that the thickness of the film is such that it's resonant with the transition of these molecules. And when you come with a second mirror, the absorption spectrum of the strongly coupled system totally changes. It goes from this black spectrum to the red one. And if you're a chemist, you know immediately that if these spectra are so different, the properties have to be different. That's obvious. This, surprisingly, is not obvious to everyone. But I think it should be pretty obvious to your audience. And so the question is, how do they change? So with the very first experiment we did was to modify, to couple an electronic transition of a photochrome myrocyanin, and in this we did in 2010 roughly, and we managed to find it to publish in 2012 after many lots of difficulties, and we showed that the presence of these polaritonic states modified significantly the photochemistry, dynamics, and yield in these reactions. And in this paper, in 2012, we pointed out that maybe if we would couple vibrations, we could modify ground state properties. And indeed, that we can. That was pure speculation, but it turns out this has a very large impact on properties, and I'll talk more about it now. So there are many things that have been looked at by so-called electronic strong coupling or coupling vibrations. And I'm going to now mainly talk, except for a few examples, I'm going to talk about how all these properties you see listed around here have been modified by coupling vibrations. Why is this surprising? Because the coupling vibrations, the perturbation, energy perturbation is tiny. It's in the order of room temperature, KT. Nevertheless, the impact is huge. And so I will start by showing you a number of examples. So here, when you do coupled vibrations, now you're in IR, so you can couple the resonant wavelengths are typically 10 microns. So now you can put a liquid inside between the two mirrors in a microfluidic system, and you coat the the mirror, you coat the windows, the IR windows of your chamber with some gold, as shown here. I'll show you an example of what we use. This is a commercial liquid IR holder, where you can inject the liquid and measure the IR spectrum. Now there's a spacer in between the two windows. So once if you coat the windows with mirrors, and then you have a spacer, the spacer can be squeezed with a screwdriver by tightening these 4 screws. And therefore you can tune the wavelength of the cavity, resonance of the cavity, optical resonance, with the absorption of the molecules, IR absorption. So the very first thing we did, which did with Joseph Moran's lab at ISIS, he prepared some molecules for us, his group. We put them inside these cavities. And here you have in red the optical resonances of the optical resonator. It's called a Fabry-Perot resonator in physics. And in blue here, we have the absorption peaks in transmission, but these are of course absorption peaks of this compound. And here we couple the SI carbon SI stretching mode, which is at 860 wave numbers. And this is a deprotection reaction. So we're going to cut this in this reaction. And we look at how the coupling to this optical mode affects the breaking of this bond, the rate of it. And so outside the cavity, it's a pseudo first order reaction. So it has a straight line if you plot a log plot. And it's outside the cavity, inside the cavity off resonance by tuning the cavity. We can move these red peaks by just squeezing the polymer with the screwdriver. Then you see nothing, no change. And then when you are coupled, you have these 2 peaks, which corresponds to the vibropolaritonic, the hybrid peaks, vibropolariton peaks. Then the reaction slows down significantly. Now, this slowdown, of course, was not the most exciting. Everybody wants something faster. But when we did the reaction thermodynamics, to our great surprise, the enthalpy of activation and the entropy of activation changed enormously. We went, here you can see the change by more than 60 kilojoules per mole. The entropy changes sign, entropy of activation, which is an indication of a large change in reaction mechanism, actually. And this was the biggest surprise of this finding, of this observation. So you can change the reactive landscape by just coupling the vibration to the cavity mode, by making this hybrid vibropolaritonic state. And this, of course, got us excited because that meant it did have an impact. I have to remind you that Rabi splitting is only 2.5 kilojoules per mole on this scale, 2.5, and here you have a 50-60 kilojoule change. So this is like a leverage effect, and we'll come back to that later on. This made us do all kinds of other things, which I'll show you now. So the next thing we tried was to see if we could tilt the landscape and induce site selectivity by coupling certain vibrations over others. And indeed one can. So a new molecule was made with 2 leaving groups, 2 different leaving groups, and which give 60% of one and 40% of two. There are 2 barriers, and the question is, can we modify them? If I show it to you, it's because we can, of course. And here you can see that we go from 60% of one to 20% of one on the strong coupling, and we get 80% of 2. This is a proof of principles that you can tilt the landscape one way or the other. And what excited the referees the most was actually this bottom left spectrum here of the action spectrum. So here you see in blue the vibrational spectrum of the molecule, and here you see when we tune across the red points, or the places we tune the cavity across these different things, and you can see that only 3 vibrations affect the reaction yield or rate. And this has to do with the fact these are the obvious ones. These are the SIC, SIO, the stretching modes, and so forth. And but it's a proof that you can use this to actually understand reaction mechanism. Here's a pretty obvious one, but if it was more complex, you could use this. Now the question is, why do we have such a, here again, I didn't show this, but the thermodynamics changes dramatically. So the question is, why do the thermodynamics change so much? And how can a tiny energy perturbation of the coupling can induce such large change in chemical reactivity? And here we found also quite accidentally that this, in studying these charge transfer complex, that this has much to do with symmetry. And everybody in chemistry knows that symmetry plays a very important role in chemical reactivity from the works of Woodward and Hoffman and other people like Bauder in the 1960s and Fukui in Japan. And so by studying this very simple reaction, we could see this occurring. So this reaction gives rise to a charge transfer complex with a peak at 350 nanometers roughly, 340 nanometers. And this is known since this was first studied in 1948 by somebody called Benesi and Hildebrand. And they did an inverse plot to be able to extract the equilibrium constant and the extinction coefficient of the complex at this wavelength. And so you normally get a linear plot when you do this, and indeed you do. And so outside the cavity, or this is the slope. And when you see that we induce, as we increase the concentration, we go from right to left, we reach the strong coupling condition. The strong coupling conditions is when the molecules and the cavity exchange virtual photons faster than the dissipation. This can be calculated, and exactly where we expected, there's a sudden transition, and there's a new slope. And from this new slope, we get a new equilibrium constant. The very surprising thing is that mesethylene has very simple IR spectrum and the vibrations have symmetries, belong to symmetry representation, E prime and A prime. And to our great surprise, we found as we scanned and we coupled different vibrations that the only thing that determined whether how the landscape shifted was the symmetry, nothing else, not the frequency, not the wave numbers of the vibration, or the type of vibrations. So here you see, and from this equilibrium we can get the free energies now, not the activation energies, the free energy, ground state free energies. And you can see again that the delta H and T delta S changes enormously depending on whether you couple E prime mode or A prime mode. If you couple E prime mode, you favor the product. If you couple A prime mode, you favor the reactants. You tilt the landscape the opposite way. And you can see here the differences in the delta G. It's a factor of 60. It's very large changes. The only way to understand that, if you spend enough time to think about it, or like we did, is that by coupling the vibration, you're changing its symmetry representation. You have to think of it this way. When you have S and P orbitals, you make sp2, sp3, sp1. The symmetry of sp2 is very different from the S and the P. This is something probably similar happening here. So clearly symmetry plays a very important role. And so then, of course, we immediately checked Woodward-Hoffman rules to see if we could change those, affect those, and indeed we can. We showed this in a paper in 2021 that we could affect the Woodward-Hoffman outcome, or the Woodward-Hoffman, or molecules that obey Woodward-Hoffman orbital symmetry rules. Now, the interactions coming back to this droplet, I told you that if it's made of hydrocarbon, a candle or a hydrocarbon of any kind holds together due to the dispersion forces, the London dispersion forces, which are driven by the vacuum field. And so we could actually see this in an experiment we did with Joseph Moran's group, and here the students studied many different alcohols, and because using Reicher's dye, which is a polarity indicator, the famous E30 polarity indicator, which chemists use. And we want to see if by coupling we chase the LUMO-HOMO transition. And indeed, if when we couple, it's very difficult to see what's going on here, but one trend is clearly observable. As we increase the length of the hydrocarbon chain on these alcohols from methyl all the way to nananol or whatever, decanol, we can see that the change in the polarity becomes larger and larger, an expectation. And this makes sense because the chain length is getting larger and larger on the alcohol, and therefore we are changing the dispersion forces. And this shows up in the polarity. Again, when we if we increase the concentration of one of these alcohols inside on the strong coupling, we see that there's a threshold where suddenly everything changes, and then the polarity is modified once and for all. This was published in JACS in last June. I don't have the reference here, but we published this already. So doing these experiments are complicated for chemists, and we understand this. I'm a physical chemist, but I worked at long terms in optics and nano-optics. And so I had a background and also a background in photochemistry. So I had the right studying chemical kinetics and dynamics. So some of these things were pretty natural to me. But of course, for a lot of chemists, it's not very easy to do optics or do chemistry, do these experiments using cavities and studying molecules inside cavities. So the other thing we have noticed is that we don't quite know sometimes. We can see changes in the material inside our cavities, but we need to monitor somehow. And so we have used physical spectroscopic techniques such as IR shift in the refractive index of the medium to follow reactions. But it'd be much better if we could use NMR. And so as chemists all know, NMR is the most powerful technique for chemistry. And so we designed a new kind of a cavity, which we have now spent about 3 years doing this, where we can actually inject, it's a microfluidic cavity. Everything is coupled everywhere. And this is so small that we can insert it into an NMR tube and do NMR directly inside the cavity. And this, of course, allows you to do also at the same time, you can measure fluorescence, IR, everything, absorption, and do NMR, which of course makes it very useful. We also, the reason I want to do this, because I expected that there will be large chemical shifts induced by VCS, by vibrational strong coupling. Why? Because obviously, if chemical reactivity is changing, then most likely electronic distribution is changed. That would be the natural thing to assume from a synthetic chemistry point of view. And to our great surprise, this does not happen. Here are some examples. This is unpublished. The paper is online, but this is unpublished, unrefereed yet for the moment. But here you see some spectrum of this diethyl benzene, black and red spectrum of proton NMR, and you see that the data is superimposable. You can do the same, then you go to carbon-13, thinking that's going to expand the sensitivity. And again, all the lines superimpose. Then we did octanol, which is one of the ones that we saw, for which we saw a polarity change. And again, within experimental error, the difference here in the fine structure is just due to the fact that shimming is very difficult for these cavities inside the NMR, okay? Because you have to, it's in a fixed position. You don't rotate the system, you just orient it in the field of the NMR. And again, the carbon-13 doesn't change. We've done this also for fluorine, same thing, absolutely no change in experimental error. And this is very surprising. Even though octanol polarity is changed as a solution, it doesn't show up in the NMR. But nevertheless, NMR is very useful. So we studied this well-known molecule that has used to monitor London dispersion forces. Notably by Professor Schreiner in Germany, who has used it to study the role of dispersion forces in different solvents. And these two groups here are very sensitive in the folded form to dispersion forces. The barrier here depends directly on the dispersion forces. And when you do this inside the cavity, you can do the NMR inside the cavity, you can measure the height of these peaks, and you can see that there's a change in the ratio when you couple the CH stretch of the molecule. And again, you see that if you're off resonance, no change. When you get on resonance under the high enough concentration that you overcome dissipation, there's a change and then it remains constant. This could only be done in the NMR. We could never observe this by other techniques. So this shows you the usefulness of these cavities. And we hope that these cavities will be used by more people to do strong coupling experiments and make it accessible to chemists. Now, a lot of other things change. I'm going to end with a few examples of things that change that are more material science oriented. For example, we showed in 2015 that you can change the conductivity of N-type semiconductors, boosted by an order of magnitude. We then showed later on that we could also boost ground state, the whole transport, because even the ground state acquires this hybrid, this is electronic strong coupling, so we couple it, electronic transition. You can change the ground state, it gets a photonic character, believe it or not, and so you can affect photoconductivity and conductivity. But more recently, people have done, former postdocs and other people have done beautiful experiments. This is by Gino Joe's group in India, and he was very much involved in our lab on strong coupling experiments. And he measures a TMD inside a cavity, and he showed that you can boost the conductivity by a factor of 60 under strong coupling. But that's not the end. Last year, there was a number of exciting experiments. There's an electrochemistry group in Japan, in Hokkaido, who showed that they can change water, ionic conductivity of water, by an order of magnitude only on coupling the stretching mode, not the bending mode of water. And not only that, the dependence on ionic strength, on the ion radius is totally modified. The original paper was published in JACS, but there are other papers that come afterwards, showing that very surprising results, but obviously very real. These are professional, real electrochemists doing this. A former postdoc in Israel at Tel Aviv University, Tal Schwartz, shown that you could boost exciton diffusion by coupling them to an oscillator, and they boost this by 6 orders of magnitude. The exciton polariton, the hybrid, suddenly moves, has probably nearly massless and moves through the material, very messy organic material, and by 6 orders of magnitude, reaching 2/3 the speed of light. The transport is ballistic of 100 micrometers. This is better than probably graphene. That means it goes without scattering for 100 micrometers. It's kind of amazing. And then another former postdoc was now a PI at Indian Institute of Science in Bangalore. He and his colleagues were trying to measure the conductivity of semiconductors under vibration by coupling the vibrations. Obviously, phonons play a role in transport, and they want to test this. And they used polystyrene as some kind of reference material, non-conductive reference materials, which showed there were no shorts in the system. And when they hit these very short wave number vibrational band, the conductivity boosted by 6 orders of magnitude. This is simple polystyrene. This is, to me, absolutely amazing. It's been online for about a year. They're still trying to get it published, and I'm sure they will. The controls experiments are thorough. But it's kind of surprising. We thought we knew everything about polystyrene, but obviously we don't know. So you can also change energy transfer. I'll just give you one example of that. Energy transfer, you can couple donors and acceptors in energy transfer experiment, and you can couple them both to the same cavity. I'm missing a slide here, but then what you have to trust me is that you can couple both, first the donor, then you couple the donor and the acceptor together to the same cavity, and you get 3 types of polaritonic states. The upper one is mostly donor, the bottom one is mostly acceptor. And you see that the energy transfer is highly boosted. This was first done by Lidji's group in England, and then we took it one step further, and then we separated the donor acceptor because these polaritonic states of the donor acceptor become quantum mechanically entangled. And then we want to see if we could do energy transfer over distances well beyond what first to predict, which puts a limit roughly at 10 nanometers. And indeed, you can do energy transfer over very long distances, no problem, inside if you have these hybrid light matter states because of entanglement. And even the first theory gets modified, and you show that it becomes distance independent. And here I can show you the thing here. So here in H is the spacer, the polymer spacer between donor and acceptor inside the cavity. We excite the donor, and outside the cavity, we get a little bit of emission from acceptor due to direct excitation, but nothing spectacular. We mainly see the emission of the donor. When we do it on the strong coupling, we see a new band appearing, which is the hybrid light matter, the emission from the hybrid lower polaritonic state, the hybrid state. And you see that the intensity of this is independent of distance. We've gone up to 150 or 200 nanometers. And this is fascinating because it means that you could do, you can engineer, you can change well-known processes in a very significant way and do energy management. So it turns out that there was an earlier paper on theory done by a group in Spain, in Madrid, Garcia Vidal and his colleagues. They had shown in 2015 that without quite realizing how it related to energy transfer that chemists do, that energy could migrate over great distances, theoretically. They had shown this on the strong coupling. It only depends on that you have strong coupling. One last example, I'll finish with one last example of a material property. We were trying to change the superconductivity transition temperature of superconductors. I used to work on superconductors when I was young, and we had worked on C60, and as a control experiment, we used YBCO. YBCO is a high TC superconductor that's not phonon dependent. So we used this as a control experiment. And we dispersed nanoparticles of YBCO that you can buy commercially in a polymer, which itself is resonant with surface plasmons. Okay, this I have not explained, but you can do something. We have developed some technique called cooperative coupling, by where we couple the solvent, which is co-resonant with a solute. And so there where we can transfer the strong coupling to a third body via the solvent. It can be a solid solvent or a liquid solvent. So here's a polymer. It's polystyrene, it turns out, and the vibrations of polystyrene couples to the surface plasmons in the dark, to their image essentially, and then they couple to the nanoparticles. And we expected no change in TC of this YBCO TC superconductor. But when we did the experiment, we dispersed the YBCO in polystyrene or PMMA. Polystyrene has a peak that's resonant with YBCO. We saw, we did a strong coupling experiment. We saw a reduction in TC of the YBCO in a squid magnetometer. And this reduction in TC seemed incredible to most people. How could this be phonon sensitive since this Cooper pairing in these materials are not due to superconductors? Indeed, and it turns out that this is due to the fact that we actually enhance ferromagnetism in these particles. The ferromagnetism, these little YBCO particles are known to have oxygen vacancy defects that are ferromagnetic, weakly ferromagnetic, milligauss. And when we couple these materials, the spins align. Don't ask me why. This we still don't know why. And you can see this ferromagnetism appearing at room temperature when you have all the elements. The gold, the resonator here is the surface plasmon, the polystyrene that couples to the gold, which in turn couples to the YBCO. And you see this spin alignment. And the spin alignment is significant because you enhance the ferromagnetism to Gauss level. So Bohr level, sorry, Bohr magneton, by a factor of 700. So this millibohr to Bohr, here you can see the things. Here we are in millibohr, and here is Bohr. We reach Bohr level. So there's a huge alignment in spin, and this enhances enhances, of course, the ferromagnetism, which suppresses TC of YBCO. Now, more recently, there have been beautiful experiments by the group of Jean Feist, Scalari, and Christian Tutti. It's all which have been published in Nature, where they show they can affect the quantum Hall effect by strong coupling. So this is not limited to to ferromagnetism. So with this, I'm going to stop. I hope I convince you that there's light in the dark. All these experiments are done without light except the energy transfer and photochemistry. And you can change chemical and material properties significantly. It's a new button to control properties that this kind of experiments open up. And there's sensors on this, some extents set up in different places. Industry is interested, I can tell you that. And if you want to read more about this field, you can read this chemist, this account of chemical research in 2016 is probably the easiest. And also a more recent thing on just chemistry, Jack's perspective that we published. We also have a review in Science, which is more physics oriented, but still it gives an overall view of all the experiments that have been done and what's behind it. And of course, I didn't do this alone. Here's an old picture where my group is much bigger. Many of these people were involved in these experiments. They've now gone on to do either postdocs or become PIs in their own labs in their own countries. And without them, I couldn't, of course, done this. So thank you for your attention.
Thank you very much for your lecture. It's very impressive, fundamental science, I would like to say. So as we discussed, I stop